Okay.
Right. So yeah, I spoiled the second slide, but oh well. Okay. So let's do this. So hello everyone. I'm Julie Bettens. I am sorry, blockchain security engineer at ChainSecurity. Just a quick word about that. We are one of the oldest smart contract audit firms. We do mostly smart contract audits, but also a lot of other things. And we've worked with some of the great people in this space to secure a lot of protocols. I've personally found multiple bugs in DRAND, but today the talk is not about that. I need to speak into the microphone. Okay. Yeah, that sounds better. Off. Okay. Okay, thank you. So today the talk is not about something I did at ChainSecurity. Rather, it is about something I did in this beautiful campus that we have in Lausanne at EPFL. It was my project for my master thesis, which was called Optimizing Commit and Reveal for Smart Contract. So this is the alternative title for this presentation. And I like to use this as a way to introduce the topic. So what do we mean by optimizing commit and reveal for smart contracts? So what is commit and reveal? Commit and reveal is a cryptographic process that is very similar to an envelope. This is a voting envelope that I have here that I will use, I think, in 2 weeks in Switzerland. And the question you should ask is, what do we expect from a voting envelope? We expect that it's not transparent, so people cannot see what's inside, but we also expect that when we open it later, we will find the same thing inside. So that means that you want, if you do this cryptographically, you want to be able to commit to a value by putting it in the envelope. And later you want to be able to reveal the value that you put into the envelope, and you want proof that it was the correct value. That means there are two security properties for commit and reveal protocols. One is hiding, the fact that the protocol does not leak any information about the message that's inside. And the other is binding, which is the fact that you are bound to your value and you cannot change your mind. Now, how do smart contracts use commit and reveal? That's the question we asked at the lab, and I will give you 3 examples which will be our motivating applications. The first one, as you can see, is ENS. If you've seen this screen, when you register an ENS, you need to do 2 transactions with 60 seconds in between. Why is that? It's because the first transaction is committing and the second transaction is revealing what the previous transactions committed. And what you get out of that is a protection against someone seeing what name you want to register while your transaction is in transit in what's called the mempool, and taking your name from you by putting their transaction in front of you. So you get essentially protection against frontrunning, which is something we will come back to. The second motivating application is also ENS. So in the beginning of ENS, there was a big auction for all the names because they knew that there would be contention. And they used also a sealed bid auction based on a commit and reveal scheme. So there was a first period where people could commit to their bids. And then there was a second period where people could reveal their bids and claim their names if it was the top bid. And we are also, as a result, using the 2 properties of commit and reveal schemes, which is, of course, hiding the bid because it's a sealed bid auction, and also being able to reveal the correct bid at the end of the process. Now, the third example is a bit more theoretical. It's an idea that has been in the space for a while, which is a way to generate unbiasable and unpredictable random numbers, not with errand, but by having multiple parties come together and all contribute their own random number. The idea is if at least one of the parties is not cooperating with the other, they will have a random number which will be mixed with whatever the other parties give, and the result will also be a random number, mixed with XOR, for example. And again, we're using the properties of the commitment scheme, which is that we hide our random values while people are committing to their own, and then later we reveal it. Note that the Ethereum beacon chain has a similar mechanism, also called RANDAO, which which is a little bit different because it uses BLS signatures instead of commit and reveal, but it also has some very similar advantages and limitations. Speaking of those, what are the limitations of commit and reveal schemes, at least hash-based commit and reveal schemes like we presented? Well, one is that it requires 2 rounds of communications or 2 transactions if you want to talk in blockchain terms, which is not ideal. It will increase, as a result, the complexity that you have in your smart contract, because you have to keep track of which bids have been submitted, whether the bidding is still open or not, and more smart contract complexity can mean more bugs. You know, I would know this is my job. And also you need to respond to unrevealed inputs. An unrevealed input is someone who does not open their commitment in time. So the question is, what do you do when that happens? And there's no really good answer, because you can't really ignore the commitment, but because it will change the result, but you don't want to wait forever. So one thing you can do is require collateral from people who commit so that they are incentivized to actually reveal. But that can also mean that they will be victim of denial of service attacks off-chain. And it also creates this situation where the last person to reveal has the most information to decide whether to attack the protocol by withholding the reveal or not. And yeah. So at the lab, we got together and we said that there has to be a better way to do this. And so that's where the project came from. And of course, I didn't start it. It was already started when I came in, but I said that for the narrative. So the project that existed at that point was called Freezing Flash Boys, where the goal was to prevent front running using temporary encryption by making a blockchain that is protected against front running. So front running, for the definition, is the process of inspecting a transaction that is pending in a mempool, and based on that transaction, inserting your own transaction in front of it in such a way as to profit. For example, by sniping an ENS name, or by buying before someone buys a token so that you can profit from their price increase, then you have to sell back after. It's called a sandwich attack. And one thing I want to highlight is that this is a weird and unintuitive phenomenon, because it breaks causality, because the front-running transaction was caused by the victim transaction, but it happens before on the blockchain. So if you were to try to explain this to your parents or someone who is not very well versed in blockchains, it would be very difficult to understand, because it just doesn't make sense, right? So what Freezing Flashboy does is it uses a threshold network, such as, for example, I'm sure, well, yeah, you can use DRAN for that, even at the current stage. So no, actually you cannot. What you would do is senders would be able to encrypt their transactions such that the threshold network, which is called the SMC in Freezing Flashboys, is able to decrypt their transaction at any time. Then they would give it to the validators or miners of the blockchain, which we call the consensus. And the consensus group would commit to the order of the transaction and run the consensus protocol until the transactions are finalized. Then finally, when the transaction is finalized, the SMC will then decrypt it and allow everyone to execute it. So the model of a model of what a blockchain is and what a transaction is that we have comes from the yellow paper of Ethereum, and it uses this formula to explain how transactions work. Sigma is the state of the Ethereum virtual machine, and T is the content of the transaction. And when you do a transaction, you are allowed to make people execute the Ethereum state transition functions, which essentially is the EVM, on the current state and your transaction, and the output will be the next state of the blockchain. The interesting thing is that they don't provide, for example, a security property such as causality. The idea that nobody should be able to change this prior state of the blockchain using the content of your transaction. But if we were to provide this security property, we would essentially be protected against front running. There's also another model that I like to introduce, which generalizes this to multiple transactions and multiple parties. The idea is that the application has some kind of state, and it also has some logic. And the logic transforms the state of the application into the new state of the application using the inputs from all the participants. And if we have such a model, we could have two security properties, one which is causality, which is similar to the one I presented for the EVM, and the second is fairness, which is the idea that people cannot withhold their inputs after they've seen other people's inputs. Now, the research goal of my thesis was to add delayed execution to a fork of Ethereum and give smart contracts temporary encryptions. The benefit that we expected to see from such an approach is, first off, complete front-running protection, then give some more credible neutrality, ideally to the blockchain in question, which we will discuss that, and implement efficient and safe sealed bid auctions using smart contracts. Now, should you do this on an L1 or an L2? I argue potentially both, because on an L2 you can experiment more easily, but L1s could also benefit from such systems, and I know there's also a lot of research going on in that direction, so obviously I'm not the only source of info on that. Now, that said, we implemented also 3 different cryptographic schemes to make this work. The first one was threshold. I will describe them slide by on their own slides, actually. So threshold public key encryption is the most similar to flash freezing flash boys. It is when transactions are encrypted individually, and the SMC, which is the threshold network, is able to decrypt one transaction at a time. Of course, it does that after the transactions have been committed and it wants to execute them. The second property is threshold identity-based encryption, where the secret management committee will generate decryption keys using identity-based encryption for every future block and release those keys when it receives a finalized block with that number. This is very similar to DRAND, except that we don't use real-world timestamp, but block numbers. And other than that, the cryptography is basically the same. The third possibility is more exotic. It's using verifiable delay functions, which are functions that take a certain amount of time to compute. So you could say it should take at least 3 seconds to decrypt this message. And the idea is we don't need a threshold network. Instead, people publish time-locked ciphertext of their transactions, and eventually someone solves the time lock puzzle and allows the execution of the transaction to be performed. Now, to go into how we implemented that a bit, the anatomy of a transaction, first off, a simple transaction has all the fields on the bottom and the to field, which is the destination address of the transaction, and the input field, which is the arbitrary call data that can be attached to a transaction. Now, if we wanted to make an encrypted transaction, we would want to replace these 2 fields with a ciphertext whose values is those fields, and add an encapsulated key next to it to be able to decrypt it. And if we decrypted this transaction, we would get those 2 fields back. We would have a reveal value, which comes either from the SMC or the VDF solver. And this should allow us to verify that the transaction was correctly decrypted. So we said we wanted to have 2 transaction types, encrypted and decrypted transaction. And the idea is to store the decrypted form of a given transaction in the block, because this allows us to use compression, like we already do today, to reduce the size of the blocks. Of course, this kind of requires a bit more computation in order to re-execute the block, because you want to re-encrypt the transaction to check that it has been correctly decrypted. But this is a trade-off between computation and storage size, which is also what compression is in the first place. Now, going a bit further into what I implemented. So the blockchain we used was a fork of Go Ethereum using the click proof of authority consensus protocol. And we created a hard fork, which I guess I'm going to call it the Bangkok hard fork now, which introduced the new transaction and the new rules about blocks. The secret management committee that we used is some academic code which implements Peterson DKG over BN254. So Kevin Charm explained a bit about BN254. And we use identity-based encryption using BLS signatures, which is again very similar to DRAND. This allows us to implement both public key encryption and identity-based encryption. The VDF for the VDF case is repeated squaring inside RSA groups, which is a fairly standard VDF design. And we use proof from Veselovsky to be able to verify the transaction. Of course, the code that we have in the implementation is not great because it would be much faster to compute it on a specialized circuit. So in the real life, you would have the problem that people would decrypt ciphertext way faster than expected. The smart contract that we implemented on top of that is a simple auction for a very valuable 1 out of 1 NFT. You can imagine that. We have an implementation using traditional commit and reveal to be used as a baseline, and an implementation designed for delayed encryption. So, and some details here. And the magic trick with this implementation is that the implementation for delayed execution is actually almost the exact same thing as an open bid auction, because it's the delayed execution and the temporary encryption that provide us with the sealed bid. So that's pretty nice. The results we got from implementing and evaluating this project is, so are the security properties fulfilled? We argue that in principle, yes, because the transactions are ordered, and then the order is committed to before the transactions are revealed. So we should have causality in the presence of almost an arbitrary adversary. And we have fairness because it's not possible to change the shadow blocks which are attached to regular blocks and contain encrypted transaction after they've been finalized. Now, comparing the methods to each other, what we get for threshold public key encryption is what triggers decryption. It is the inclusion of the transaction in a finalized shadow block. How much data do we need to add to verify the re-encryption? We need 212 bytes. So 128 bytes and 64 bytes for elliptic curve points, and 20 bytes to include the sender address, because otherwise there's a dependency that you can't decrypt without the sender address, but you can't get the sender address without decrypting. And it costs 192,000 gas to verify a transaction, which is something we should additionally charge to people who do transaction to account for the additional computation. This is also, yeah. And we think that this method does front-running protection best, because even if a transaction is not included, it's not decrypted, so this lets traders keep their alpha. Now, when we look at threshold identity-based encryption, I've highlighted the differences. What triggers the decryption is the finalization of a block, regardless of if the transaction has been included a bit before or has not been included. So that's important. The size of the witness is a bit lower, in part because the decryption key is shared across blocks. So if this is done properly, we should be able to store it only once. The gas cost is the same because the cryptography is the same. And we think it's great for auctions because everyone will want to target the same block. And it's also less work for the SMC. And the verifiable delay version of that, so the change is that the time on the clock that's on the wall is used for the decryption trigger. The witness size goes up as a result of it being RSA 2048. And the gas cost, however, is lower based on benchmarks and to stay consistent with EIP 1108. In principle, this would be okay for auctions, but we know that this is not cryptologically ready because VDFs have not been studied very well, so it's possible that there could be a way to compute them faster than we expect. Now, from the perspective of the application, what happens? So we no longer so this is the sealed bid auction. We no longer need to have a bid limit because in the initial version we did, because you need to overcommit to over-collateralize your bid. And so that means that if your bid is higher than the limit, you have a problem. We've also made it much more capital efficient because your capital is never really locked because the transaction happens atomically. Well, it can be locked if you win the auction even temporarily. However, we've still doubled the gas cost per bidder in the SMC case. In the VDF case, it's slightly equal, despite the fact that we do one less transaction. And the execution latency has increased. And this is also something you feel when you run the demo, because tools like Foundry expect an execution receipt when they send an Ethereum transaction. And on the delayed execution system, those take longer. Now it would be possible to solve that, but that would require changing the tooling a little bit. So this is a difference between the theory and the practice that we can highlight, because in theory, if you ask someone who is a bit more academic, they will say that you can never trust a transaction if it's not finalized, because the point of finalization is to make sure that a transaction is not going to be reorganized and executed differently or dropped by the network. But in practice, what people do is they have this rule that if you get one or two confirmation on a non-finalized block on Ethereum, this is pretty good. And so in this case, this means that we've altered their workflow a lot by adding delayed execution. We could help this, for example, by making finality faster on Ethereum. Now, other things that we've broken for applications, one of the things is that transaction simulation is harder to do because whatever you do, you will have a lot of encrypted transactions that are already being committed that will go in front of your transaction, but you have no idea what they do. So the starting conditions of the simulation may be different. This is something that you have to be careful about. The gas estimations are also much worse, in part because of the same problem. And execution receipts take longer to appear, as I mentioned, because they need to wait for execution. So the drawbacks of this type of approach that we can include are that it would require a fork, that it breaks EIP 1559 relatively badly because EIP 1559 needs to know how much gas was actually consumed so that it can adapt the pricing quickly. There's also no refunding of unused gas because otherwise it would open a denial of service vector where you could reserve the old block but not pay for it. There's also an added reliance on the SMC, which it seemed from existing debate that this is unacceptable from the perspective of Ethereum because they don't want to expect the threshold network to stay online, which is why they use this different scheme that is called RenDAO. And we would lose most of the benefits of the MEV extraction actors that exist today. And you might say, this is strange, are there benefits to having MEV? Well, yes, because when you have someone who looks at the block and simulates transaction to extract profit, what they will do is they will liquidate people on lending protocols very promptly because it's profitable. They will also arbitrage pools, which is better for having accurate prices. And there are systems like flashbots where you can reduce the number of failed transactions that eat up space in the block because people submit their transaction with the instruction to simulate it before including it. And as a result, the failed transactions are discarded by flashbots or similar services and don't end up on chain. Now, future works that could be performed as far as this area is concerned, could we reintroduce some of the benefits of MEV? So there's some guy who has a blog somewhere who worked on inclusion lists and mentioned that maybe we should consider the inclusion list, so inclusion lists are a weaker version of our system on Ethereum where proposers would give a list of transactions that must not be censored by the block builders that do MEV. And it's being considered for Ethereum. And it's kind of a simpler version of shadow blocks because inclusion lists do not guarantee order and currently do not support encrypted transactions. But so what this person said is that we could consider that actually the inclusion list is the bulk of the block, it's the real block in a sense, and the area where the block builder can add some transactions to extract MEV is actually a smaller part of the block. And so if you see it that way, you could say the shadow block becomes the block. We leave 10% additional gas for MEV at the end of the block, and we build our blockchain like that. And we would get this fast lane transaction that can do arbitrage much easier. Now, should we show contracts, the smart contracts, that is the decryption key from the EVM? I think there are two interesting reasons to do that. One is to allow apps to enforce that delayed encryption is used, or at least delayed execution. And that's because, like we said on the previous slide, we could add a fast lane transactions, and that could actually break the fairness property of some applications. So they would have to defend against that, and they could enforce that people use delayed transaction to interact with them. And the second thing is it will provide synchronous randomness. And this is easier to explain here because you probably all know DRAND, and you probably noticed that decryption keys also serve as random beacons and vice versa. So in our case, we reuse our decryption keys as random beacons. And in the case of time lock with DRAND, they do the opposite. They reuse the random beacons as decryption keys. Now, another area of further work would be, what about trusted execution environments? Can we use TEEs to make this more secure? The idea would be that the TEE would either in threshold or as a single TEE hold the decryption key. This is kind of interesting because it would force someone to at least locally commit a slashable offense from the point of view of the consensus protocol. So for example, double sign a lot of Ethereum blocks so that they can produce a fake chain. And the TE would enforce that the signatures are valid. This is interesting, but if the TE is in a box somewhere and the adversary has control over that box, the evidence would probably never come out of the data center. So this could be combined with the threshold network so that there's a lot more chance that the slashable offense is actually detected by an honest actor. And could we encrypt more fields? Because you probably noticed that we only encrypted the destination address and the call data. The difficulty with that is that in order to see that a transaction should be included in a block, it needs to be signed properly and be able to pay the fee. That's why some of the fields are left unclear. But can we solve this? Yes, we should be able to solve this with zero knowledge proof. If we can have a system where we prove in zero knowledge that the encrypted transaction can be included in the block. An interesting consequence of that is Does this mean if, for example, you have a centralized L2 with a centralized sequencer, does that mean that the centralized sequencer loses the ability to censor? I argue that not exactly, because they can still decide to not include any transaction, or what they could do is require an additional ZK proof that proves that you are not a censored entity. But the interesting consequence of that is that we've created a system where anyone who generates a proof knows exactly what the censorship criteria is. So this is a way to transparently, verifiably censor your rollup, which is quite interesting. Now, having said that, I am getting to the end, so I would like to thank these three people, Professor Brian Port from PFL, Yolan Ramayer from Rendezvous, and my colleague Shufan Wan for working on this project before me. And to conclude a bit, temporary encryption is interesting because it allows us to do things with blockchains that are difficult to do otherwise. Front-running protection, sealed bid auctions, some forms of DAO voting, as well as randomness generation. So for that, there are also other solutions as we've seen. But there are some challenges in implementing that, especially in existing networks, and it can disrupt existing workflows for applications. Two things that can help us do this better are cheap on-chain execution. So if the gas is cheaper and you have to pay for the re-encryption, and fast finality so that you have less latency. Now, if you want to reach me to discuss this or to discuss something related to chain security that I can forward to the rich people, you can search these three letters on pretty much any platform, Discord, Telegram, Twitter, etc. And I will conclude by giving you a link to the code for the demonstration. And I expect your questions here. Thank you. Yes.
Have you benchmarked it at all, and do you know what kind of overhead it adds to infrastructure?
Have I benchmarked and measured the overhead? So there are different types of overhead. Some of it is witness data, and some of it is on-chain execution, which I've benchmarked a lot. The other question is, can we have a secret management committee or a set of VDF solvers that are fast enough to keep up? And it seemed in my test that this was not the bottleneck, but this would eventually be a bottleneck, so this should be evaluated. But also those things are getting more efficient, so it's difficult to say for sure. Or I accidentally pressed the button. I hope it's not an issue. Okay. Someone else?